Okay. In this lecture, we are going to see how do you do that state-based representation of transfer function in electrical system, right? Now, then how do you convert the electrical system into state-based representation? So, the conversion of electrical system into state-based representation, conversion of the electrical system into convert electrical system to state-based representation. So, here now you have to consider what is state, what is input, what is output, then we are going to find out, right? So now here you have to consider Kirchhoff voltage law equation for a given electricity. First, you have to write the Kirchhoff voltage law for the given electrical network or system. Then second, choose the current through the inductor. So inductor, here we are having current through the through the inductor. What's the current? Then across the capacitor, what is the voltage? Right. So here across the capacitor, what is the voltage? So that is VC. So this voltage across the capacitance. So this is actually we are having voltage across. So that VC is 1, right? So that is voltage across capacitance. That is VC. The capacitor is C, right? Then here inductor is here we have to consider now L. So L is here we are having now that inductor. So current through the inductor. So that current and the voltage across the capacitor, current through the inductor and voltage across the capacitor as here you have to consider as state variable. Right. Now choose the voltage drop across the resistance, right? So that resistance in that resistance across the resistance, what's the voltage drop? Voltage drop means here this is voltage Vs. Then what is the voltage between here? Then in the difference between these two is actually the voltage across the resistance. The voltage across the resistor, voltage drop across the resistor, voltage drop, right? So then Vs2, then some V. So this is one nodal point, right? So that Vs minus Vc is the drop across the resistance. So that one is you have to consider as output. Now the exciting sources, right? Exciting sources. So what here the exciting source is Vs, source voltage. That is taken as input. So the input, output, and state variable we are given, right? So that one is here. How do you do that? By a electric circuit, right? Now you consider a simple electrical circuit with RLC circuit. So here resistance, inductor and capacitor. Resistor, inductor and capacitor. Now here you consider now this is one loop. So now current through the loop is you have to consider as I, right? Then voltage across the resistance is what's the current across the resistance, then I into R is actually voltage across the voltage drop across the resistance is I into R. Next here we are having the inductor. So current through the inductor. So we are having now. So now here what is the voltage drop across the inductor is actually L dI by dt. So dI by dt is the differentiation of current. Then here we are having now that capacitors, right? So capacitor is actually we are going to, so through the current, so we are having now the current is going to, current is actually coulomb is we are having now current and the time you call it as actually we are having a charge, right? Now that integrating the charge you consider it as voltage, right? So that is here we have to consider now that one by C and integral of I dt. So this is actually voltage across the capacitance. So this one is VC, this is VL, and this is we are having VR. So the voltage is dropped here, here, and here, right? So this is VC, this is the voltage across the inductor. Then here we are having now the resistors. So that is here. So the summing of that all drop you consider as the source voltage. The source voltage here, starting from here to end here we are having 0. So this is the drop. The drop is going to be summation. So R into I, then L di by dt, and 1 by C integral of di by dt. Integral of di by dt. Now voltage across the capacitance, so that is VC, right? I told you that one. The voltage across the capacitance is here. VC is equal to that one, that part. 1 by C and integral IDT, right? So that one is here. Next, then here this VC is going to be replaced by here, right? VC. Next, we are having that whatever it is here, VS and VC. Then voltage across the capacitance and resistance. So here we are having now this voltage across the capacitance is one variable, and current through the inductor is another variable, right? So that one is here. We are having now that LDA by dt is in the left hand side and Vs in the left hand side. Then we are having now the right hand side is we are having that Vs, and then so here we are having Vs minus Ri and minus Vc. So that one is here LD. So voltage across. Then this L is going to come to here, right? So now we are having in the differential form dA by dt. Then L is going to divided by on the right hand side. So how do you get now? This VC is voltage across the, so that the total sources here, voltage across the resistor, then here voltage across the inductor, then we are having now voltage across the capacitors, right? So that is we are having summing up, right? Now this VC, we are having now this VC and I are variable. Then you have to take that one as here, and the VS is we are having considered as the input. So input, then these two are variable. Now, here we are having that equation is in the form of dI by dt equal to Vs by L minus R by Li and minus 1 by R Vc. Then here you have, how do you represent in the state-based representation, right? So I told you that one, that I current is one variable. So that variable in the form of x1. Then Vc is another variable. Then is x2. Then dA by dt. So I is x1 means the dA by dt is differential of the current. So the differential is represented by the dot at the top. So this one is actually dI by dt. So x dot I, right? Then here we are having the input voltage Vs as U. So now we are representing that one x1 and x2 is state variable and U is input. Then we have to consider the output is voltage across the capacitance and current through the. So here we have the voltage. Here we are having voltage across the resistance is output, right? Voltage across the resistance is output. Now here, how do you do that one, right? So x2, what is x2 here? X2 is the variable, right? So that one is here voltage across the capacitance. X2 is voltage across the capacitance. Now if you are differentiate on both sides, so what you will get now? This one is x2 dot, then equal to 1 by c. The integral part is this integral part is cos of, then this is we are having now x1, so x2 x1. Next, that here we are having now the dA by dt is x1, then here 1 by L into U is here you are considering as Vs, right? Then we are having now R by L and I is x1 and x2, right? Now we are having these two equation, right? Now that equation is going to represent as a vector form, and then you will get now that one as, so x1 equal to x1 dot equal to minus R by L x1 minus 1 by L x2 plus 1 by L U. So that x1 x2 are variable. Now that x2 is here, we are having 1 by C x1. Now you have to consider as output is here voltage across the resistance, I into R, voltage across the resistance only. So the I is we are having considering is x1, so x1 into R. Now you have to represent in the matrix form. It's an easy way, right? So how do you represent that one as, here we are having now x1 dot, then here we have to consider now that R by L is x1. So that one is R minus R by L. So this is the coefficient. This coefficient you have to write. X1 coefficient is we have to write here. So you are multiplying this x1, right? Then we are having now x2 coefficient minus 1 by L. We have to place it here. And then we are having that x2. In that x2 we are having only x1 term. There is no x2 term. So 1 by c, the x2 term is 0. The 1 by c only the coefficient of x1. So that is we are placing now here. And the x2 term is not there. So you have to put it as 0. Now Here, this is the input term. Only that in that x1 we are having that input term. So here you have to take that one as the coefficient 1 by L, and the x2 term there is no input. There is no input. So you put it as a 0, right? Then the input you consider as ui. So this is the state-based representation in matrix form, right? So for simple electrical circuits, now we are getting now the state-based representation in matrix form.